Hello, I welcome you all to this series of lectures on Z transform. In the previous lectures, we have talked about what is the need of transform, what are the different types of transforms. The different types of transforms are according to the different types of signals, and there are different types of signals, like we can have a set of continuous time signals and a set of discrete time signals. In this also, there can be periodic continuous time signals, aperiodic continuous time signals. Also, there can be periodic dt signals, aperiodic dt signals. So depending upon the type of signal, we have different transforms like Fourier series, discrete time Fourier series, continuous time Fourier series, Fourier transform, discrete time Fourier transform, continuous time Fourier transform. However, we saw the limitations of Fourier series and Fourier transform. We saw what we call as a Dirichlet conditions, which cannot so the signals which do not satisfy the Dirichlet conditions, they are not Fourier transformable. Hence we go for one more transform, which is called as the Z transform for discrete time signals, whose equivalent is Laplace transform for continuous time signals. So we saw what is meant by Z transform. It is a power series equation, and it is characterized by a region of convergence, ROC. We have seen how to compute the Z transforms for causal signals, anti-causal signals, non-causal signals, and what are the properties of region of convergence, which are very important. Then we saw what are the different properties of Z transform, how these properties can be used to simplify the numericals on Z transform. Then in today's lecture, we will be talking about the inverse Z transform. So what is inverse Z transform? So normally when we are having a signal x of n, okay, so this x of n is in the time domain, right? So x of n is in the time domain. So when we transform this signal to the z domain, we take the Z transform, okay. So when we take the Z transform of this x of n, we get what we call it as x of z. So x of z is called as the Z transform, right? X of z is called as the Z transform. Now inverse Z transform is that you are having this x of z and you have to find x of n. So you have to take the inverse Z transform of this x of z. So x of z is given over here. So you have to take the inverse Z transform and you have to obtain the original time domain signal. So going from time domain to frequency domain is forward transform, Z transform, and coming inverse from frequency domain to time domain, that is from x of z to x of n, is what is called as the inverse Z transform. So remember, in the numericals of inverse Z transform, we will be given x of z along with the ROC, and we have to find out the time domain signal, okay. So that is called as the inverse Z transform. To compute the inverse Z transform, we will be looking at two different methods. One is called as the partial fraction expansion method. Another is power series expansion method. This power series expansion method is also called as a long division method, LDM. Okay, long division method that we will be seeing subsequently after studying the partial fraction expansion. So in case of partial fraction expansion method, okay, we can express x of z as a sum of partial fractions, and then we can find out the inverse Z transform. So in the numericals of inverse Z transform, we have to always remember that we need to understand and we need to remember the important Z transform pairs, which are very, very important. Okay. So this table gives us the important Z transform pairs. So we should know, okay, what are the time domain representation and the frequency domain or the Z domain representation of these basic signals. So we have to learn this. So this means that if the sequence is del of n, the Z transform is 1, okay. So the Z transform of del of n is 1, and ROC comprises of the entire Z plane, all Z, okay. Similarly, the Z transform of u of n, the Z transform of u of n is given by 1 upon 1 minus z raised to minus 1. This we have already solved the numerical. In the numerical we have found the Z transform. But you have to remember this Z transform directly here, because these pairs will be used directly in the numericals for inverse Z transform. So the inverse Z transform of the Z transform of u of n is given by 1 upon 1 minus z raised to minus 1, okay. And the ROC here is important. The ROC is mod of z greater than 1. One thing you have to note, very important, that whenever there is a causal signal, the ROC is always in the form of mod of z greater than r. Okay, it may be, so since it was u of n, it is greater than 1. If it is any other thing, it will be greater than 2, greater than 3, greater in general greater than a. So this greater than is important. Okay, so we can remember one thing, should conclude one thing, that when there is a causal signal, the ROC is always exterior of the circle. This is the property of ROC, if you remember. And when there is a non-causal signal, okay, so when there is a non-causal signal like minus u of minus n minus 1, okay, so we see that the both the z transforms are same. Okay, so you can see here, this is 1 upon 1 minus z raised to minus 1, this is also 1 upon 1 minus z raised to minus 1, but their ROCs are different. There is a huge lot of difference between the ROCs. Here the ROC is mod of z less than 1. Here the ROC is mod of z greater than 1. So this is the main difference. Okay, so this solidifies the concept that two different signals can have the same z transform. Two different signals here, u of n and minus u of minus n minus 1, these are two different signals. Their z transform is same, which is 1 upon 1 minus z raised to minus 1, but their ROCs are different. Okay, so it is the ROC which gives uniqueness to a signal. Okay, so whenever you are specifying the z transform, you should also specify the ROC. So when I write the z transform as 1 upon 1 minus z raised to minus 1, then there will be confusion whether this z transform corresponds to this signal or this signal, because the z transform of this signal is also same. But when I specify that the z transform is 1 upon 1 minus z raised to minus 1 with the ROC mod of z greater than 1, then it has to be this signal only, it cannot be this signal. Similarly, when I specify mod of z less than 1 as a ROC, then it has to be this non-causal signal, it cannot be a causal signal. That's why it is so much important that whenever we write the Z transform, we should write the ROC. If you don't write the ROC for a Z transform, then that Z transform has no meaning at all. Okay, so we have to remember this. So whenever there is a causal signal, whenever there is a non-causal signal, we write the Z transforms, we write their ROCs. ROCs are very, very important. Okay, then this is the time shifting property. Okay, so since here it is del of n minus 1, so it is z raised to minus m. If it is del of n plus m, it will be z raised to m. This is what we call it as a multiplication with an exponential. So a raised to n u of n, the z transform is 1 upon 1 minus a z raised to minus 1. So this a can be anything. It will be 2 raised to n, so it is 1 upon 1 minus 2 z raised to minus n, 0.5 raised to n, so 1 upon 1 minus 0.5 z raised to minus 1. So this is again a standard pair. We have to remember the standard pair. Such pairs will come again and again, and since this is the causal signal, the ROC is mod of z greater than a. So greater than sign is important. Similar signal is here. The z transform is same of both the signals, 1 upon 1 minus a z raised to minus 1, but their ROCs are different. Here the ROC is different. So less than specifies that it is a non-causal signal, greater than specifies that it is a causal signal. Okay, so similarly you can have a signal like this, n into a raised to n u of n. So you have to remember the standard pair, which is equal to this. Okay, so here two properties we have to apply: a raised to n multiplication with a raised to n and multiplication with n. Okay, so we get this z transform. So you can remember this z transform, you can find out the z transform by solving this equation. But for inverse z transform, we have to remember these pairs so that we will use these pairs directly in our numericals. Okay, this is for causal signal, so it is mod of z greater than a. This is for non-causal signal, so it is mod of z less than a. Okay, similarly when it is a cosine function multiplied by u of n, this is the whole z transform that we have to remember for causal case. Okay, this is sinusoidal for causal case. Okay, this is multiplication with an exponential r raised to n, then this is the formula, used formula. Okay, so these will not be used much in our case, but this will be used a lot of times. Okay, in our all the numericals that we are going to see for the inverse z transform. So these standard pairs will be the most important pairs that we will be using for our inverse z transform by solving for maybe partial fraction expansion method. Okay, for partial fraction expansion method. Okay, so with this introduction to inverse z transform and the different important z transform pairs, in the next lecture we will talk about the partial fraction expansion method. Thank you.